in memory of Dharkar sir. We have here Mayank Vaihwaya sir as our chief guest of today. I welcome Mahesh sir. I welcome Rekha Gurpade madam. I welcome Bhole sir, Kiran Kolvalkar sir, and also many others who have joined in. Rekha ma'am would um, tell me better. So now I hand over to Bhole sir to talk about IAPG.
Thank you, madam.
Welcome, Bhole.
Uh, this is our fifth lecture for RMD series, and on behalf of IAPT Sabarsi 08B, Mumbai, I welcome all. The series was started quite a long ago, and it was dedicated to a dedicated professor, RM Dharkar. And every year, at least twice, we meet and discuss about academic activities and so on in this particular series. The IAPT as such, which was established in 1984 by Professor D.P. Khandelwal and others, and has now grown like a very, very big organization, having more than 10,000 members throughout the India and outside. We have around 23 RCs and some RCs in that RCs also for the administrative purpose, and Mumbai sub-RC happens to be one of the sub-RC for Maharashtra. The IAPT as such conducts large number of examinations which spans for the students from school as well as junior college, degree college, for teachers and so on. The competitions which are organized, which includes the essay competition, photo essay competition, and then the innovative experiment competitions and so on. There are a large number of competitions which are also organized at regional level and sub-regional level also. And the winners are always given prizes and certificates of participation also. The website, which is a very, very up-to-date website now, which is having a title IAPT, indapt.org.in, which gives lots of information about all the events which are organized throughout India by various RCs. And at the same time, it also has a collection of, you can say, the competitions, the essays which are prized in competitions. It also has collection of essays, events, photographs, videos. So it is a good resource for the students and the visitors of this particular website. They will get a lot of information available there. At the same time, the IAPT is particularly dedicated for improvement of the physics education in India. And it's not only for the teachers, but it's for the students, teachers, researchers, and so on. At all the levels, the activities are going on throughout the year. It has been seen in the last 5 years, the activities are spread like anything. And there is still a lot of scope, we feel, to go ahead with. For more information, one can visit the website indapt.org.in. I also mention here that the regional, sub-regional council Mumbai has been organizing 2 series of lectures. That one is the RMD series, RM Dharkar, Professor RM Dharkar Memorial Series. At the same time, we do have another series in the name of SC Pradhan, and we do have such type of lectures organized for throughout the year, which will be conveyed to you on the group. Thank you all.
Thank you, Bhole sir. So today we are having symmetry in mind and matter, by Mayank Vahiya sir. So, to introduce our guest, we have Mahesh Sethi sir. Mahesh Sethi sir, kindly tell something about our Vahiya sir.
Good evening, everyone. Professor Vaya retired from Tata Institute of Fundamental Research, that is TIFR. He worked in the field of high energy astrophysics. He also took interest in application of astronomy and archaeology in the later part of his career and started a dedicated group in archaeoastronomy there. And they have contributed a lot of work in that. Professor Vaya may be known to many people as he has given numerous popular level lectures in astronomy, mathematics, physics, and also many may have listened to his famous lectures. Many teachers, especially, may have listened to his famous lectures, Science and Society, as well as the Atoms to Astronomy. He is an IIPT life member. He was coordinator for Astronomy Olympiad program of India and led Indian teams multiple times. He has been a great motivator and was instrumental in starting talent nurture program for Indian Science Olympiad teams so that they pursue science in our country. Uh, After retirement, he was director of School of Mathematics at Narsi Monji Institute, and now he is associated as emeritus professor at Atomic Mass Spectrography Center in Mumbai University. Welcome, Professor Vaya, for your lecture.
Yeah. Thank you very much, Mahesh, for that generous introduction. Yeah, I've been friends with so many of the audience members. It's great to be back. I want to thank Mahesh, first of all, for inviting me to give this lecture. A smaller version of this I had given to students who completed the course recently, IEPT program in North Mumbai, and then I decided that I would expand that to include more things for the teachers of physics because there's a lot of interesting ideas that go with symmetry. And symmetry is a subject that we do not formally handle in the sense that when we teach physics, we do not really take symmetry arguments for various things. And symmetry is very illuminating perspective. So that is what I want to do first. But more importantly, it is an honor for me to give this Dharkar Memorial Lecture because Professor Dharkar, I was very fond of Professor Dharkar, and it's an honor to meet him and to talk to him, etc. So he, of course, made some significant contributions to the development of voluntary physics examination and pedagogical improvements in physics education. He also started the National Science Examination in Physics as well as National Graduate Physics Program. He organized entrance examinations for Physics Olympiad all over the country and more than 1,000 centers. Within a matter of a year or two, he had 1,000 centers all over the country where students took entrance exam. It was phenomenally successful. It is in this context that I met Professor Dharkar for the first time. I was very fond of him. I respected him greatly. And his approach to physics, to education, and to general welfare of students and teachers was truly exemplary. His enthusiasm was not only infectious, but behind that enthusiasm, we could see lay a man who could deliver on his enthusiasm, and that is what made it so beautiful to interact with him. It was always a pleasure to interact with him, and so with those words of respect for and recognition of his community, his contribution to the community, and his love for the community. Let me put a little garment on his photograph at least and begin this lecture. And those who have not worked with Professor Dharkar have really missed something in life. So, Professor Dharkar, we really miss you. Coming back to the topic of the day, the topic is symmetry. And this is a beautiful example of architectural symmetry where you can see the symmetry. But symmetry is at a lot of places. This is the CERN detector. This is solar oscillations. This is galaxy formation with black hole mergers and so on. This is crystallography. This is relativity. This is particle physics. And all of them involve symmetry. And what I am going to do is to show you how symmetry works in all these ideas. Symmetry has a simple definition. If you go and ask AI, it's a symmetry is a balanced and proportional, is the balance and proportional corresponding arrangement of parts of on opposite side of a dividing line, um, line, center, axis, creating a very harmonious and mirror image effect depending on where you put your mirror. It indicates that the subject remains unchanged, invariant. In physics, symmetry essentially suggests that the entity is invariant against the transformation, and very quickly becomes conservation laws and all that, making symmetry a very powerful way of looking at physics. And that's what is going to be my second part of the talk. In art, symmetry is simply geometrical symmetries. Time symmetries are repetition of sequence, but in nature, you will find symmetries in nature, in science, especially physics, chemistry, biology, astronomy, and particle physics, and in human activities. And we'll look at examples of all these things. Um, so for symmetry as a balance proportional corresponding to arrangement of parts, geometrical symmetries are obvious. They are reflective symmetry, rotational symmetry, translational symmetry, helical symmetries, which are both translation and rotation combined, scale symmetries. Other symmetries include glide, reflection, and so on. So, in geometry and visual aspects, symmetry is an obvious entity that we come across in a variety of places, and they do make life simpler in many ways. Origami has a beautiful tradition of making symmetrical designs, which provide insights into how human imagination and human creativity works in terms of folding paper and creating interesting animate objects. Nature itself uses symmetry in a very profound manner. Human beings themselves are attracted to symmetry, and symmetry is something we catch very quickly in our brains. Animals that move in one direction, maybe forward or backward, but essentially one direction, all of them have a symmetry along the line of their movement. So this is an example of peacock, but you can see think of all the animals that you can, and you'll realize that they all have symmetry along the direction in which they move. And things like octopus, which can move in multiple directions, have symmetries along those other directions. In the wild, the concept of symmetry is not a trivial one. After all, the human beings are all life is designed to eat, not be eaten, and reproduce. And the reproduction has to be of the best of the genes available in a given pool. And how do you test the best of genes? So symmetry becomes the first test that human mind performs on any potential partner to see whether they get at least their symmetry right before we consider their fitness and other things. So it is more profound than simply appreciating beauty. It is a way of evaluating a potential person with whom you are going to interact, and symmetry plays a lot of important role in it, to the extent that our brains are actually hardwired to see symmetry. Even a child, even an infant who is not a few months, less than a year old, a few months old, who has not yet been contaminated by our values of culture and identity and so on, will identify symmetry and asymmetric structures. So there have been experiments where an infant was put in front of a projector, and pretty faces were projected on the screen, and it had a lot of toys to distract it. And as long as you are projecting pretty faces, the child would keep looking at the faces. The moment you put a face that is or something that is not symmetrical, the child would get distracted and start playing with toys. The idea of being attracted by symmetry is built into our brain. So the ratios of distance between the eyes to ear and head, etc., are all very well focused for a particular kind of symmetry. And some of these symmetries, of course, come from requirements. The separation between the eyes has to be such that the stereoscopic effect can be effective to a reasonable distance. If you keep the eyes too close, then then our ability to do a 3D comprehension would be lost, and so on. So various reasons why symmetries come up, but symmetries are there everywhere. And it is at one level, therefore you would think that geometry etc means that the idea of symmetry is an artifact of human mind. At another level, it is purely a very natural response of our senses to our environment. At another level, it is and as I will show you in the second half, it's a fundamental organizing principle of nature to have symmetries because they go with conservation laws and other things, invariants and conservative laws. And broken symmetries are, in fact, a very delightful subject. We will talk about it towards the end. So in art, the symmetry is simple. There is reflection symmetry, there is rotation, radial symmetry, there is translational symmetry, there is near proxima symmetry, there is inverted symmetry, and other kinds of symmetries, rotational and so on, helical symmetries and so on. And of course, asymmetry is also a part of symmetry, in some sense breaking of symmetric, where you are expecting symmetry and removing it also produces a kind of sensation to the eyes. Ishar, of course, is the ultimate in asymmetrical symmetric drawing, if you wish, where you can see this famous staircase where everybody seems to be climbing but nobody seems to be climbing, and it's a beautiful example of symmetries. And most of Escher's painting have drawings have this kind of ideas of symmetries playing in to give you visually very challenging arts. There are, of course, tiles that are symmetrical. In this case, the symmetries are not so obvious, but symmetries are there. There are a variety of kinds. Fractals are the ultimate in symmetries because they are scale invariant. Looking at a fractal, you can never say how big it is because it is infinitely symmetrical across size scales. In architecture, Taj Mahal is the ultimate in symmetry. And I checked with Google AI as to which is the most symmetrical building in the world, and it came out with Taj Mahal, which is not only symmetrical in terms of the vertical axis, but the right down to the minarets and all the details in it. If you take an aerial view of Taj Mahal, also there is a degree of symmetry which extends beyond the building itself, including the two buildings on the side and so on. Symmetries are something that has always attracted us. Then there is mathematical symmetry. Mathematical symmetries, apart from geometrical symmetry, are symmetries of mathematical operations, and these are some of the obvious things. They preserve the specific property of a group. In general, is a kind of structure in mathematics that have their own kinds of symmetries. For example, there are even and odd functions which are very in a very specific manner symmetrical. Then there are symmetries of algebra, matrices, and so on, which have their own properties and capabilities. Gaussian distribution is the ultimate in symmetric as far as thermodynamics and a lot of other equilibrium phenomena are concerned, where you get this kind of Gaussian or Bell symmetry, as it were. Nature, laws of nature are direction insensitive. So, in other words, if you for the short time, if you forget about gravity's effect, essentially nature has no specific directions in which things are there. It is completely symmetrical against directions, and nature is also in some sense symmetric to space and time, and that actually is a serious problem for physics, because most laws in physics are time reversible, and therefore time is an impossible entity to define. Most physicists won't know what time, or rather no physicist knows what time is. We know that is one of the four axes of the space-time continuum, but it has a very peculiar property of moving in one direction, and that direction is impossible to define. The only way you define is that the entropy of the universe keeps increasing, and that's a very poor way of defining. But really, we have no good definition of what is time, and that is because the universe's laws are symmetric to time and space, except entropy, which keeps increasing. In general, physics laws are time symmetric, and so if you replace t by minus t, you still get solutions which are valid. Each observed symmetry, therefore, is a reflection of some entity that causes the symmetry and is associated with some kind of conservation law. Broken symmetries are often called violations of symmetry, are also insightful, and we will discuss those aspects also in detail. Hence, a study of symmetry is in nature is a fundamentally different study from all other ways of approaching our understanding of nature. Symmetries in logic are obviously, if you take binary operators against p and some operator q equal to something, and if it is equivalent to Q and the same operation on P, then O, then whatever that operator may be is a symmetrical operator. So conjunction is symmetrical, disjunction is symmetrical, exclusive OR is also true. Then there is biconditional OR, there is NOR, and so on. All kinds of logic gates have their own symmetries. The key characteristic is that they are commutative, so they can be interchanged, and they are a functionally complete set. If you take NAND and NOR are functionally complete, it means that the logical sequence is complete, and therefore those symmetries help. Symmetry in chemistry is somewhat more profound in the sense that it underwrites essentially all aspects of interaction in chemistry. So chemical molecules, we draw them symmetrically, but they are largely symmetrical in structure, and that gives useful ideas of redundancy and chemical analysis and so on. So, for example, we know that large chemical molecules can interact with other large molecules in such a way that there is energy minimization in the final structure. And it happens at a speed so much faster than what statistics would say, that there is somewhere within these molecules a kind of knowledge system which knows that if a molecule of a particular kind comes, it should be connected to a particular set of nodes in order to make the new molecule that you want. And that is probably symmetry driven, where the molecule nature decides where which molecule should be fitting on a given molecule. Proteins, folding, and so on are all examples of how a symmetrical molecule self folds itself to be chemically most effective, rather than have the entire molecular structure available for chemical reactions. Uh, it is rigorous to understand that symmetry explains fundamental observations in quantum chemistry and is applied to areas of spectroscopy and crystallography. And the DNA structure, of course, came because it was somewhat easier to identify because of its symmetry. And its application in various areas is very useful. Also, chemical properties depend on whether whether the created molecule is symmetrical or not. So, this is an example of a molecule where if it is the molecular connections between, rather, atomic connections between molecules is symmetric or asymmetric, will give you different relative energy in terms of kilocalories per mole, and the reactivity will different. So the same chemical molecule we know is not, the chemical formula of a given molecule is not sufficient to define what kind of energetic reactions it will do. It is its shape and its symmetry is built into that shape that decide how chemical molecule will behave. So we have examples where chemical molecules get folded differently, and when they are folded differently, their properties are very different from those of other kind of folds. So there it counts. There is, for example, para-electric phase is something where the symmetries are broken and you lose symmetry. The moment you restore the symmetry, you get back your para-electric phases, para or ferroelectric phase, depending on which one you want. But broken symmetries can change the properties of material without changing their content. Symmetries in biology are somewhat obvious, in some cases not. Symmetry in biology refers to symmetry observed in organisms. External symmetry can be easily seen by looking at organisms, like I said. Even symmetries are used to exaggerate shape in nature. So this butterfly is essentially a puny little thing, but the way it is designed, it gives you a feeling that is much larger and therefore keeps the predators away. Internal features also tend to show symmetry, which makes repairs and maintenance much easier when there are issues and complications. In biology, the notion of symmetry is also used explicitly in describing body shapes. Bilateral animals, including humans, like I said, have a preferred direction of symmetry across their entire body. In natural selection, symmetry is the first test of fitness of a potential mate, and therefore it is hardwired into our brain. I already said this earlier, and it decides the fitness as a first testing, as a first test of fitness of a set of genes. Plants and animals have radial and rotational symmetries and plants in order to attract bees and insects have all kinds of beautiful symmetries, which make them attractive to the insects and birds, so that they may pollinate the plant. So symmetry is used very heavily by plants to attract pollinators. Biological information is coded in the form of DNA. The double helix is a ladder, and at some stage, that in some sense, that is a symmetric structure, but in many senses it is not, in the sense that the two legs of the ladder of DNA is the same, but the steps are not symmetrical. And it's one of those curious cases where symmetry is not symmetry. And I will come to that a little later. So if you look at biological systems, you will see all kinds of shapes and sizes in nature where symmetries are used very heavily in order to make them simpler and more attractive. Symmetry in psychology is another issue. Visual images processing is faster if the object is symmetrical, and human reaction to a system actually increases significantly if the object that you put in front of them has a vertical axis of symmetry, and makes it faster for humans to grasp the details. If you give an asymmetric object with a similar content, it takes the human brain a little longer to fathom the entire structure. So both behavioral and neurological studies have confirmed that we have a special sensitivity to reflection symmetry, and we catch it much faster. Humans can pick up a symmetry in much more quickly, in 100 to 50 milliseconds, compared to 700 milliseconds we take to fathom something that is not symmetrical. This is in extraspatial. This is done in the extraspatial region of the. There's a dedicated region of the brain which specifically catches symmetrical symmetries in systems. And as you can see, it involves both the right brain and the left brain together to figure out something. That is what makes it faster. Normally, if the image is not symmetrical, then it is the right brain trying to compare with other images and trying to make sense out of it, or consulting the left brain, if the case may be, to understand the shape. If it is symmetrical, then it lights up our entire brain to very quickly catch a symmetrical object, and that is how we have our reflex time going down so much. In general, large parts of visual systems seem to be involved in processing visual information, and these areas involve similar networks to those responsible for detecting and recognizing objects. So when you're recognizing or detecting an object, the visual images first go through and test for symmetrical, because if it is symmetrical, the brain can very quickly identify what it is rather than something that is not symmetrical. So in our visual system, it is hardwired not only for an infant, not only for genetics, but in general, identifying symmetrical objects is much easier for us. Then there is symmetry in social sciences. In general, relations are asymmetrical. But when the relations are between people of equal standings, they tend to be more stable and more symmetric. So symmetrical relations hold up much better than asymmetrical relations in behavior and interaction. The game theory that essentially talks about how human beings react seriously depends on whether there are symmetrical reactions or asymmetrical reactions, in the sense that um, if you for example play this game of a set of squares on a computer screen, where the white ones are of one kind, black ones are of one kind, and if you write a rule saying that one white between two blacks makes the white one black, and vice versa, and then randomly start the game, you will eventually see that it will settle down into 50% white and 50% black, even though the equilibrium will be dynamic. So game theory also suggests that eventually we reach an equilibrium which is symmetrical between various properties, or the way human beings react with various systems. The golden rule of behavior is that principles of treating other like you want to be treated, and this maxim itself has significant symmetry built into it. It is also there in religious and cultural identities, because we do tend to identify with similar people with similar cultural background. It is the ethic of reciprocity in some religion. Others, in different religions, treat this affections differently. But essentially, that idea of symmetrical relations and symmetrical value systems makes a lot of difference in human behavior and interaction. Symmetries in software. refer to architectural designs and operational balances where components are interchangeable, behavior is invariant under transformation, and therefore the programming becomes so much easier. The key aspects of these symmetricals are architectural symmetry. If you have your basic logic, like the DNA molecule itself has some basic string, and then it keeps calling subroutines in other parts of DNA to get anything activated. Similarly, a program written with calls and interactions much more efficiently than a completely single long program. And that architectural symmetry right at the beginning of the designing of a software will make a lot of difference on how well that software can be used over a long period of time. Object oriented design systems that applies when the object of the same class are interchangeable, or permutation symmetry, will also make a lot of difference in the way you do the programming. Design patterns in softwares work much better, and if they're symmetrical, those programs are easier to debug, easy to use, and easier to understand how they're doing. Process simulation also uses symmetrical ideas to be able to replicate the working of a system and to do troubleshooting and so on. So in many aspects of software, um, symmetry ideas are pursued either consciously or subconsciously to make the programming more visible. And essentially, what AI does also is to look for patterns. In hardware, in electronics, also we use symmetries, and they can simplify complex design analysis, identify identical voltage potentials, and so on. So there are multiple things you can do. Mirror symmetry is obviously one big important thing. If you have a circuit board where the central line is the ground potential, and then you put circuits on either side, there is a sense of symmetry that comes in, which makes debugging of the electronics easier. A folded symmetry is a particular kind of mirror symmetry where there is a single axis against which you fold your electronics to make debugging so much easier for hardware. Equipotential points are obvious points of symmetry because if you connect those 2 points, it makes no sense. There is no current between them because they're equipotential surfaces. So redundancies in the electronic circuits, their relative efficiency, their relative voltages, etc., all of them make a difference. So when you design a circuit, if you begin with the concept of symmetry behind in your mind, then your final product will be so much more understandable. And is in case of troubleshooting, it's easier to do that. Symmetrical circuits can be analyzed, and separating them into two identical hulls also helps in electronics. Symmetry and beauty of science has a special value. So, in science, symmetry represents an organizing principle. The presence of symmetry reveals redundancy in the information content, and that is useful. Symmetry also explains more knowledge with less data having to go into it. Transformation under which laws of nature remain unchanged are all conservation laws. So, symmetric transformations in anything for which you can write or an unambiguous procedure, and which, when performed on any observation, leaves the observation unchanged, will give you a lot of insight into what is happening. Scientists are prone to take relations between beauty and symmetry further, and as we will see that in many cases, they are in fact obsessed with this idea of symmetry. There is even a serious discussion in science whether experimental validity should be necessary for calling something scientific, and whether in the absence of data, just the fact that the theory is symmetrical and beautiful should be accepted as valid. So string theorists, for example, have string theory actually is a model, and standard model of particle physics is actually a theory, and yet string theorists has been pushing for some time to give their theory a veneer of recognition as formal science, because it is symmetrical, even if there is no experimental data that confirms the predictions of string theory. So even within science, there have been arguments as to whether this can be used as a criterion. It is not accepted. Most people would simply laugh at it, but there are people who are making serious attempts to do that. Symmetry in physical science is about invariance and conservation laws. And let me take some examples. So symmetry is the best bedrock of particle physics. It dictates the laws of nature, determines the types of particles that can exist, and defines how they interact through fundamental forces. In 1915, Noether proved that continuous symmetries correspond to conservation laws. So if something is symmetric against, say, translation, etc., it immediately comes out as a conservation law in physics. Time translation symmetry, for example, leads to conservation of energy and so on. Space translation gives you conservation of momentum, and rotational symmetry gives you the conservation of angular momentum. Angular momentum is conserved in a system, in an isolated system. Space momentum is conserved, and energy, of course, is conserved. Gauge systems, we will see a little later, give conservation of charge. That charge can also neither be created nor be destroyed. Space-time symmetry. These are related to particles, how particles move and exist in four-dimensional space-time. So there are two kinds of space symmetries. One is Poincare symmetry, which we've been using since Newton's time. It includes translation, rotational, and boost in terms of accelerator and so acceleration, so on, and it defines the mass and spin of particles. But since Einstein's pioneering work, Lorentz symmetry has also come into play in physics in a big way. It ensures that laws of physics remain the same irrespective of frame of reference, and even the Lorentz transformations do not violate these conservation laws, um, even when transformations are applied. And these become very useful tools for doing further science. Symmetries in physics are also called invariants. Things do not change under the following conditions. So translation, it doesn't change, rotation, it doesn't change, and so on. And gives an idea of transformations. It allows you to make arbitrary coordinate systems and arbitrary origins, because there is a space-time conservation or invariance in nature system. So you can put your origins anywhere, you can put your axis directions anywhere, and so on. The important symmetries in physics are symmetries in crystalline material, continuous symmetry and discrete symmetries in space-time, internal symmetries in particles, and supersymmetry in physical theories. And we will come to those a little later. These concepts have become one of the most powerful tools of theoretical physics, as it has become evident that practically all laws of nature originate from symmetries. P.W. Anderson said that it is only a slight overstating the case to say that physics is a study of symmetry. It is one thing to do is to look at them as Newton's laws and Maxwell's equations and Lorentz transformations. The other one is to approach it entirely from the perspective of symmetries. Noether's theorem simplifies that every continuous mathematical symmetry, there is a corresponding conserved quantity, such as energy, momentum, angular momentum, current, or whatever you have it. And symmetries, therefore, are another window to what is conserved entities or what is invariant entities inside. Wegener's classification says that symmetries of the laws of physics determine the properties of particles that are found in nature. And we have had several cases, especially in standard theory, where particles have been predicted based on these conservation laws, that if these laws are conserved, then a particular combination of quarks should be allowed, and therefore a particular kind of particle should be found, and they have been found later on. So symmetries have actually been predictive in many cases. Then there are gauge theories, which physicists very fondly use. These are called special unitary groups, which define these symmetries. These symmetries do not happen in physical space, but in internal mathematical spaces, and they reveal conservation laws which are underlying any process. So, for example, standard model uses three kinds of symmetries in order to understand the working of nature. SU1 symmetry is linked to electromagnetism, and that leads to the production of existence of massless photon, which produces interactions over long distances of space and time at velocity of light. SU2 symmetry gives you the link between the weak forces, and given their distances and their limited range, we know that they must be governed by this W and Z bosons, which are massive, and therefore they, within the uncertainty principle, their range to which they can go is limited, and therefore weak forces must only act on nuclear level. Similarly, strong forces are used in quantum chromodynamics as SU3 symmetry, and then people have tried higher symmetries for other kind of explanations um, to try and understand physics. So color charts, quarks, etc. People have tried to use higher levels of symmetry, but SU1, 2, and 3 are primarily used and have been used successfully to determine particles. The dream theory is a supersymmetry theory called SUSY. The theoretical symmetry that relates to fermions and bosons. As to what is the fundamental symmetry between fermions and bosons, we have no idea what the symmetry looks like. It suggests that particle has a super partner of a much higher mass, against which this particular symmetry can be seen, but we have no idea what this supersymmetric partners will be. So there are a lot of people who would want to believe that the dark matter problem of astrophysics is generated by the supersymmetric heavy particles of fermions and bosons that give you the corresponding heavy particle. It explains the hierarchical principle. It explains why Higgs boson is so light and super partners must be there, whose interactions cancel out the massive quantum correlation that we otherwise see in inflate the mass. The mass of Higgs boson is very light, and there must be a super partner to it that cancels out the massive quantum correlation that we get. Again, these are on scales which our experiments can't reach, so we have to just speculate on them. And there's an idea of grand unification of a strong, weak, and electromagnetic interaction, which should merge into a single force at uh, extremely high energies. Again, this is a theory that we do not have a formal nature of. We do not know what SUSY looks like, but there are people who are trying. So string theory is one of the attempts to talk about these supersymmetries in nature, but it remains yet to be proven. So if you look at particle physics, you have this Higgs boson, and that Higgs boson essentially at the beginning of the universe, the upper picture above the central line is the picture, I can't see my laser pointer, is the picture of Higgs boson at higher level of energy, and when the symmetry is broken, it comes down to a ground level, and at ground level we can see its effects on in terms of our mass and friction and so on. Then there are baryons at a higher energy which tend to merge. The left-hand symmetries are given by SU2 doublets, and left-handed symmetries are also given by SU2 sublets for both neutrinos and leptons as well as quarks. And at lower energy, symmetries are broken. So you have protons and neutrons and so on, and you have these particles as separate entities. The symmetries that go with each of these, uh, the SUSY essentially goes with, let that box go. SUSY essentially goes with color, and it gives you the idea that there must be a graviton which gives you gravity. Then there are SU2 particles which are defined, which give you weak interactions of various kinds. And then SU1, which gives you the gamma ray and photons rather, and the electromagnetic radiation. And it turns out that the way nature is organized is that the velocity of light, even though we associate it with electromagnetic radiation, essentially it's a fundamental property of space-time which does not allow information to pass at velocities faster than c, whether it is gravitational, whether it is electromagnetic, or so on. They are the only two forces around with zero mass mediator, and therefore they have an infinite range. But even within that infinite range, their velocity will be equal to velocity of light. It cannot be less, it cannot be more. But that is what these symmetries define. Higgs boson, in some sense, is what gives you inertia and mass, and you can think of it as if a fish swimming in a swimming pool feels the friction but doesn't know why. And you can imagine some fish getting together and getting a heater so that they can convert water into steam and eventually separate out water molecules, which give you the resistance, which makes you realize that it is this water that is giving you resistance. In some sense, Higgs boson is a similar kind of entity which gives us resistance in the universe. But even then, questions like why is inertial resistance same as gravitational resistance are questions that still need to be answered. To move further, therefore, if you take all the forces in the universe, in the beginning, of course, there was only one force about which we know very little. Then strong and nuclear forces come into being, electromagnetic forces come into being, and today we can see weak nuclear forces and gravitational forces. And we know electromagnetic forces are not going to degenerate. It is not that electricity is going to be separate from magnetism, even at the lowest energy level. They remain coupled. So SU1 gives you the electromagnetic force, SU2 gives you the weak nuclear force, SU3 gives you the strong nuclear force. And the hope is that the three of them will eventually get merged into a single idea of a supersymmetric entity with its own mediating particle to give you an idea about why the universe works the way it does. Gravity has always been a nuisance in some sense of the word, because unlike other forces, gravity is purely attractive. And therefore, the moment so when there are two gravitating objects, they must fall into each other or run away from each other. And Keplerian velocity is a very rare condition, but otherwise objects must run away from each other or bang into each other. Given that singularity, mathematically, it has become difficult to handle that because all equations tend to go into singularities and you can bypass singularities. But these attempts have not yielded the kind of results we wanted to see. Then there are discrete symmetries. Unlike continuous symmetries, there are discrete symmetries like flip and mirror operations. And the three important ones are charge and parity. Mirror image of something and charge and particle and antiparticle charges of being opposite. Time reversal in some sense is also a discrete operation, but in time itself is a continuous entity. And there is a CPT theorem, which is a fundamental law stating that all physical laws must remain same if C, P, and T are all reversed simultaneously. But if you reverse only C and P, then you have a problem. So if you have a particle, Rabi incidentally cyclic behavior of two quantum systems in an oscillatory manner will essentially oscillate like this, and there'll be symmetrical probability wave that will go out. Against parity, it should remain the same. Against rotation, it should remain the same. And against time, it should remain the same. Or against particle hole, which gives you both rotation and parity. It turns out that this symmetry does not work. And we will come to that breaking of that symmetry a little later. Then Keplerian velocity is a very peculiar specific case of rotation. And in order for an object to remain in a stable revolution, it must have this very specific velocity. Otherwise, you end up with this greatly symmetrical shapes of parabola or hyperbola, which is the most common shapes as far as gravity is concerned. But you can have circles and ellipses under very specific conditions. Also, the center of mass of these two objects in that case must become a stable point of symmetry in terms of mass distribution on either side of that central point, the center of gravity of the combined system. Then symmetry in astronomy. Astronomy talks about matter scattered all over the place, and yet astronomy relies on a lot of symmetries. The first one is rotational symmetries. Everything rotates. Stars rotate, sun rotates, galaxies rotates, everybody rotates and gives you, as a first order, a symmetry, actually a break in a spherical symmetrical, because you end up with this disks and so on. Orbits of rotation in many cases of circular symmetry. So if you have a non-rotating object in the universe, essentially it's a perfectly symmetrical object. A spherical object which is non-rotating. The moment you introduce rotation, you actually break the symmetry against the third axis, and you end up with accretion disks and disks around the star. So we are a part of the broken symmetry of the sun's object because sun rotates. We rotate along the equator of the sun. Astronomy also depends heavily on homogeneity. That is, the quantity is the same wherever you look, even if there are local anisotropy. It assumes that overall the universe is both homogeneous and isotropic. It is the same wherever you look, and it is also isotropic wherever you look. And these are two very fundamental assumptions of astronomy. So if you look at, for example, hydrogen spectrum, whether you look at it in your lab or whether you look at it from coming from a distant galaxy, the relative line distribution of the hydrogen line will be the same. The individual lines will have blue shifting or red shifting or whatever the case may be, but the relative separation between various hydrogen lines will always remain the same because the universe is homogeneous and you can get it from anywhere because the universe is isotropic. And that is what tells us that the fundamental universal constant, the velocity of light, the electrostatic forces, the various forces, etc., that we have not changed over time. The hydrogen spectrum from early universe looks exactly identical to hydrogen spectrum in your lab, and that is because the universe is homogeneous and isotropic, and fundamental constants of the universe have not been changing. So in some sense, it gives you the symmetric principle that works on very, very large scale. But they do break on small scales. We have planets and we have sun and so on. And also astronomy is completely asymmetrical with time. I will come to black hole discussions a little later. And that is underlying theory of space-time that we end up with. The general relativity is again symmetric with time. So relativity and symmetries are another set of issues. Special theory of relativity states that two objects moving with respect to each other at constant speed are completely symmetrical. And that ends up with that twin paradox about which train oh God. It is symmetric across time. That word Annie has got deleted and gone into the next line. I'm sorry. So it is symmetrical across time and coordinate transformations. It is so there is no right or wrong clock. There is no direction of the clocks. Each clock works in its own standard manner, but it may appear to be different depending on your apparent velocity with respect to the other object. But as long as it is constant velocity, it is symmetrical. General theory of relativity, on the other hand, says that accelerated frames in gravity are identical. So it establishes a symmetry across a force and what was classically a mechanical system. And that changes a lot of things. And I will show you, we'll talk a little bit more about black holes and stuff like that. It is showed that light is an electromagnetic radiation bends with gravity. And two very different fundamental forces now get connected because it turns out that velocity of light is a fundamental property of space-time, and it is not specific to electromagnetic radiation or only to gravity. Given the similarity between electromagnetism, it implies that light is a fundamental property of the universe rather than a specific number associated with oscillating electromagnetic fields. It establishes that velocity of light is not just a speed of light, but it is a very fundamental number um, about information going across space-time with being carried by an object of zero mass. A non-zero mass will not reach that velocity, and a zero mass object cannot move at a slower speed. I mean, Cherenkov light, etc., are specific conditions, but in general, it will not slow down. Then there are symmetries that aren't. We would think they are symmetrical, but in reality, they are not. Brain, for example, for a long time, people used to think that left brain and right brain are symmetrical. They are not. They're functionally, they are very different entities. DNA molecules are a ladder, but that spacing between the steps of ladders is so much different that it is not a symmetrical object. Non-crystalline solids obviously are not symmetrical. In many of these cases, there are very specific regions where nature has chosen not to have symmetry. Everything is not symmetrical. Non-symmetric structures have their own importance. But breaking symmetries is what I want to touch in last 10 minutes. While most of the laws of physics are symmetric against the arrow of time, thermodynamics breaks this symmetry. The only way you can define forward direction of time is through thermodynamics, saying everything goes on from lower entropy to higher entropy. It's a bad definition when you get down to details and you get down to worrying about black hole and entropies and stuff like that. You really get into serious trouble. Take an example of a spinning top. I don't know whether I don't have the picture. A top that is spinning is perfectly symmetrical with respect to its spin axis, But the moment it slows down, that symmetry breaks, and a top that is not spinning is not symmetrical anymore. And those broken symmetries as a function of energy will tell you what about the function of that particular object is. And therefore, so broken symmetries are a very useful entity in physics. And the birth of the universe itself is non-symmetric. If you have broken symmetries are critical, because if you, for example, had a perfectly symmetrical state layout of a city, you would never find your homes. These cities therefore make orthogonal streets, etc., but then eventually break those symmetries with street names, shop names, direction markers, etc. Otherwise, you would never be able to get back home. Broken symmetries are critical to some of the information content. Broken symmetries do two things. They tell us about the one who broke the symmetry, and they tell us about, give us a roadmap to explore why the symmetry is broken and what it does. Examples of broken symmetries are many. Suppose if you appear on Earth and look at the sky looks completely blue, and you cannot differentiate between north, south, east, and west. But the moment you have the sun in the sky, it breaks the symmetry, and now you can define what is north, south, east, and west. So in many cases, broken symmetry actually reveal information that would otherwise be difficult to decipher. So broken symmetries have their own powers and capabilities. When you discover the sun, for example, like I showed you in that picture, that broken symmetry gives you a lot about the nature. Similarly, gauge theories and symmetries show you a lot of information. Broken symmetries, this is the example of top, it should have come there, where as long as it is spinning, it is perfectly symmetrical. The moment it falls, it breaks the symmetry. And this is how the Higgs mechanism work at high energies. The weak electromagnetic forces are unified. The universe cools, that symmetry gets broken, and therefore you have mass in the universe at a later date. Early, when the universe was born, it was essentially massless. It was just this question of quarks and so on. CP violation, I've already talked about. CP violation is what I will come to next. Sorry. So conservation laws at atomic level have various entity, and CP symmetry was assumed to be valid. It turns out that we discovered that CP symmetry is not valid. And what I mean is, I'll just go to the next slide because that illuminates it better. That CP, the charge and parity, both if you change of a particle, the resultant particle that you get is not identical. The combined changes in charge configuration, making positive charge negative and taking the mirror image, gives you completely different particle, and therefore the particle and antiparticles actually have different properties. And that explains why the universe, when it was born, was predominantly one kind of particle that we call particles, and that there were not equal number of particles and antiparticles. It comes from the fact that there is CP violation in nature. Discovered in 64 through neutral kaon decay, but now we know that it is a fundamental property of the universe, and that is how it is made of particles and not particles and antiparticles in equal numbers. So what I mean is that if you take a charged particle, and if you sort of take anti-neutrino, and if you mirror it, what you get is a very different world than when you try to just do mirror and charged particles. There is a difference between how it works, and that breaking of that symmetry tells you why the universe is full of charged particles rather than of particles rather than being equal mix of particles and antiparticles. Okay, so while barrier number violation observed in terrestrial experiments suggests that this must be the case, and if you try to manipulate that to try and get CP violation out, you end up with other absurdities that the temperature of the universe has to be much higher at earlier stages, which is not possible. So, but we still don't know what exactly is the source of this CP violation. Why are we not getting the same particle back? We do not know. Black holes in astronomy are another set of interesting objects. There are four types of black holes. There is a very Schwarzschild black hole, which is non-spinning, non-chained, and that is stable. Then there is Kerr black hole, which is spinning and uncharged. Then there are charged black holes, and there are charged black holes which spin, and they give you completely different things. Quantum mechanics tells you that vacuum is not complete. It is filled with virtual particles, and Hawking showed that these virtual photons in particular can suddenly come alive in the gravitational field of inside a black hole, and one of those particles can escape while the other one is captured inside, as a result of which black holes will evaporate. And that Hawking radiation showed that eventually energy from a black hole will gradually evaporate because of vacuum fluctuations, where the radiation is spontaneously created and part of it is lost to the black hole. So charged black holes are another interesting feature. So a normal a non-rotating, a non-rotating black hole is completely symmetrical. The moment you add rotation to it, you end up with accretion disks and disks around it, and you can look at how the spin of the two, the black hole and the accretion disk, are related. And in fact, the whole system becomes more complicated because gravity can bend light, and such a strong gravitating object, the bending can be even more significant. So you end up with a black hole, a symmetrical, a non-rotating black hole looks like this, while a rotating black hole looks like this. And then when you add charge, there is even more fun. I mean, these are, I'm going to skip this slide. When you add charge to it, the whole system changes completely, in the sense that um, charge also cannot be created or destroyed. So inside this black hole kind of material, where we used to think that there will be infinite density, charge will come into balancing, because unlike charges repel. And therefore, inside the Schwarzschild, inside the event horizon, we suspect that there will be another sphere of electrostatic charges, which will prevent a complete breakdown of the black hole mass into the center. And because of the fact that black hole radiation evaporates over a period of time, this event horizon will contract. And when it comes in contact with the electrostatic sphere of inside the black hole will essentially evaporate in a whiff. So symmetries and broken symmetries can do a lot of things for you. There are examples of broken symmetries in life. In life, for example, things like Vastu Shastra tell you that Earth's magnetic field is rotation, and so on. But I'm going to skip that particular slide. So we have symmetries everywhere. But the question is, are we overemphasizing symmetries? Symmetries are intellectually very attractive because they give you a lot of conservation laws and stuff like that. But many theories are just for their symmetries. So conservation laws, laws of molecular interactions, information coding in biology, etc., um, go essentially depend on symmetries. And symmetries are defined as part of this theory. Um, and local symmetries of space-time are used for a variety of extraction principles. But some symmetries can also mislead. For example, there is a strong case can be made that over a period of time, and I'll come to this book of Hosenfelder, who says that I think that she makes a case that physics has become too obsessed with symmetries and mathematics, and that we need to look beyond it because we are at a dead end. And I'll come to that in a minute. So nature is not bound. If you go back and go to a very primitive definition of symmetry that I gave in the beginning, it is essentially visual. And visual symmetry is a classically human brain product, and nature is not bound by that kind of ideas of symmetry. Whether those laws of gauge theories, etc., are something independent of human mind, and whether they've existed and we have discovered them, is a question you can ask. But we are currently over seduced, as it were, by the idea of symmetry. So in field of particle physics, where there's a paucity of data, scientists have often relied on symmetry as an argument. Like I said, string theorists want a recognition as a theory because they think it is symmetrical and beautiful. So sometimes it misses you, prevents you from seeing reality properly. And nature may not always be symmetrical. So if you overemphasize symmetry, also you can get lost. So there's a book called Lost in Maths, and beautiful how the beauty of maths leads us astray. The book is a criticism of how fundamental laws of physics work. If you are interested in this topic, you must get this book. It's not a very expensive book to get. It emphasizes that things like our obsession with supersymmetry is just silly. Our emphasis on the idea of symmetry is so overwhelming that we are not looking for other explanations about how forces merge and so on. There is an argument that symmetries are naturalness. Again, that is a bias which is sort of driving us away from looking at real universe. Multiverse is another idea which exists simply because we want symmetries. And it may just be a natural absurdity to think in terms of multiverses and so on. And she says that physics seems to have taken a wrong turn because of this overemphasis on mathematical beauty in what it is. And that physics in principle, in fact, she goes on to say that physics concentrates on a few problems where symmetries and these kind of ideas can be used, ignoring a lot of other fields which may give you a good insight into how nature works. Okay, so physics, so we need to be, even though beauty and symmetry and invariance, etc., are powerful tools, you should not be overwhelmed by them. There are problems where these kind of arguments don't seem to work. Neutrino, for example, is a very classical example of a non-zero mass object that moves at velocity of light and it also oscillates between various kinds of neutrinos. And just ideas of symmetry and mathematical elegance are not going to get you there. Dark energy, again, is something, a completely different entity we have no idea about. Dark matter have been associated with Susi particles, but they may not be Susi particles. A lot of evidence suggests that this dark matter is ordinary matter that is not emitting light. Stability of vacuum. We talk about vacuum and vacuum fluctuations that produce particles and antiparticles, etc. That basic concept is implicitly designed on symmetries and stabilities and stuff like that. There may be completely different arguments for it. Similarly, fundamentals of quantum mechanics, multiverses, because various probabilities are open, are driven by our desire for these symmetries and understanding nature in a particular perspective. Somewhere down the line, we need additional perspectives, nature of space, time, and so on. Standard model, for example, works on everything on Earth, but it does not explain 97% of the universe. Dark energy, dark matter, etc. are examples. So we have to worry about relations between charge and mass. Mass cannot exist without charge, and charge cannot exist without mass. It is a dichotomy we really do not understand. Whether electromagnetic forces at what level are same, we do not know. Relations between inertial mass and gravitational mass is another place where we struggle. So essentially, the best idea may be to stay with Occam's razor, which says that we should only assume or make a minimal set of assumptions in order to explain every phenomena. And symmetry is not an assumption you need to make a priori. If it comes out, fine. If it doesn't come out, fine. But nature is far more complicated, and nature is also not obliged to make itself understandable to us. So we should go back to somewhat simplest or direct ways of thinking, which do not bind us to this symmetry, which has served us well. But maybe it may be time to think beyond symmetries in understanding the world. The bottom line is symmetry has different meanings in different contexts. The human brain is designed to identify visual symmetries. Mathematics gives you geometrical symmetries. Physical sciences completely change the meaning of the word symmetry. And many of breakthroughs have come from this idea of symmetries, but we need to sort of worry about going beyond symmetries. Okay. So there are people who would believe that physics has been led astray by this excessive emphasis on symmetries, and we need to go back to simplicity. Thank you very much for listening. I have overshot my time, and I'm sorry for that.
Thank you,
Thank you very
sir.
much. Yeah, we didn't even realize that. So, thank you very much for such a wonderful presentation. The talk is open for discussion. Anyone has question, you can unmute and ask, or we can. Meanwhile, there was a news which said that now it is. I mean, Susie's. I mean, it is. I mean, Susie is not there. That is confirmed in experiments. Is that right, or what is it? What is the
Yeah,
status?
so Susie has claimed, for example, for that maybe there are more kinds of neutrinos, etc., and those things have been seriously brought down. So CERN clearly says that there are only 3 kinds of neutrinos and so on. So there are issues with Susie, whether it is our quest that is taking us there or whether it genuinely exists, and that is a point.
Is there anybody? Anyone? One can ask.
Yeah. Mahesh, you wanted to say something?
No, I wanted to ask, this is regarding the earlier part where you talked about the social sciences and you said the golden rule of behavior, game
Yes,
theory, ethical reciprocity.
correct.
So the question is this, that are there any kind of game theory models, okay, where say for example, is a reciprocal honoring society has more chances to survive over say
Yes.
hierarchical society. I mean, just
So,
take example, say Potter World, Gryffindor versus Slytherin. The Gryffindor is more reciprocal honoring society, whereas the Slytherin will be more structured, more hierarchical society. So, I mean, does one have? I mean, are there any kind of models in game theory which show that
so there are game
over
theoretical
a long time
models
one will
which,
survive more? Yeah.
yeah. So there are game theoretical models which put altruism against crookedness. And it turns out, so the idea is this: the basic fundamental place where game theory starts is that there are two thieves who have committed a big crime about which police doesn't have evidence. So they arrest them for a smaller crime, isolate them at two different places, and then tell them that if you give us evidence about the other person's big crime, we will let you go. So for the small crime, both of them will get 1 year punishment and both of them will be out in 1 year. But if one of them stitches on the other, he gets 0 year punishment, but the other fellow gets 3 year punishment. And the question is, under what condition will the one fellow give up on the other fellow and throw him to the wolves, as it were? And that, how do you define that, etc.? So one will be altruistic and say, no, I will not give you evidence against my friend and I'll suffer 1 year of jail. On the other hand, the other fellow may say that, no, no, I want to save my life. This is the evidence against the other fellow and you let me go. So this kind of balancing of forces or attitudes, you can program into a machine. Essentially, the white block, black block example I gave you is a cruder version of the same thing. And it turns out that if a society is full of, it has too many crooks, it will not survive. If it has too many altruistic people, it will not get anywhere. Because then the temptation of the crooks will be much larger. And eventually you get a 50-50 stability where there should be equal number of altruistic people and equal number of crooks for the society to be stable.
There is there is
What
a,
I wanted to show was that the word symmetry has so many different meanings.
yeah, it was
So there is a question. Ek minute,
yeah.
the Suhani has put a question in the chat saying that symmetry is also associated with stability, because symmetry also means that the forces are balanced. And anything that is symmetrical is likely to be more stable. And therefore, it is natural that stability will come from symmetry.
There's another question: can black holes provide slight proof of life in the cosmos? Yes.
Sorry?
Not, there's another question in the chat box. Uh,
Yes.
can black holes provide slight proof of life in the cosmos?
Black holes will not. Black holes, in the sense, are see, life is simply, I mean, at purely physical level, it is just a collection of molecules that can self-replicate at the crudest level. Then they become more complex is another part of the story. But essentially, life begins when with self-replicating molecules and the entire molecular pool where this kind of self-replication is possible. DNA on its own, for example, is a useless piece of molecule. It will do nothing. It is like a library in a college. It has all the information, but is completely useless unless somebody goes and reads that information. So you need a whole bunch of supporting molecules in order to extract information from from this DNA and so on. Given that conditions and given that black holes are very nasty with any order and destroy everything into one gigantic hole, it is unlikely that you will get information about life in the universe through black holes. That would be my honest and straightforward answer. But I can give a horribly complicated answer in the sense that we don't know time, and we know that there is no time on event horizon. So there are people who have wondered whether time itself is a projection, localized projection, a holographic projection of this two-dimensional time on the space-time that gives us the sense of three dimension and the universe and time and so on. If that view is correct, and it's more a mathematical game rather than anything serious in physical entity. But if that was true, then probably it would even projection would tell you whether there are universes, livable conditions around and stuff like that. Stability, I already answered. Yes, symmetrical systems will be more stable. So, for example, in monsoon, when they cut the trees in Mumbai, symmetry is one of the arguments they give. Equal amount of tree material should exist on all sides of the tree so that it does not topple off in case of a strong wind from any direction. So yes, in stability, symmetry is a major issue. And even our gardeners practice it when they prepare their trees for monsoons and so on.
Yes. Dr. Boy has suggested 2 books on symmetry in the chat box.
Yeah, there are 2 books.
Yeah.
Unfortunately, Mir publication died with
Yes.
Soviet Union. They were a great source of
but
fantastic
the
books.
childhood, yes. In the college days, we have seen that book.
Yes.
Sir,
Yes, sure, sir.
one
Go ahead.
question.
Yes.
We normally, as a physicist, we normally try to find out symmetry in asymmetric objects. Is it
Yes.
because of we are heavily loaded with conservation laws?
We are probably biased. And in many cases, that bias has worked in the sense that we have, I mean, when Newton, for example, wrote down his Newton's laws of motion, symmetry was not in his mind. It was a very classical explanation of experimental phenomena. Later on, we have seen symmetries and realized how it can be built up. On the other hand, when particle physics went crazy and a whole bunch of particles were found, people were wondering how to organize them. So the standard model comes with symmetry as an argument to organize all the particles that you are seeing in your accelerators. So there, symmetry was used a priori. At the beginning itself, it was used, incorporated to try and understand all these particles that are formed in accelerators. But Newton's laws, symmetry was recognized post facto. So it has varied in different conditions. But SUSY, for example, is driven by our desire for this symmetry. And it's not working is true. String theory, in some senses, driven by arguments of symmetry. I mean, simply go to 5, 6, 7, 8 dimensions and so on, but try and preserve that symmetry. Dr. Aluwalia has a question.
Yes. Please go ahead, sir.
Yeah, thank you very much, Professor Wahi, for a wonderful lecture, particularly because this year we are also celebrating 100 years birth of Abdus Salam. You have been talking
Yes.
about standard model a lot.
Yes.
And I think it's a kind of, I would see it as a tribute to him also, your lecture.
Correct.
And that's very, very interesting. You know, when as a physics student who is not a student of particle physics at all, you know, we'll just end up with this idea that symmetry and conservation laws are closely linked. Beyond that,
Yeah.
you know, he or she has no perception of how beautiful symmetry has been exploited using group theory, and mathematics is indispensable actually. So whenever you look at any particle physics, you know, concept, you will always find they start talking about those groups, etc., which looks really weird to a person who is not used to all those things.
When I first had particle physics talking about SU3, SU2, SU1, I was quite confused.
Yes.
Yeah.
And normally only particle physics people feel that, okay, we are the masters of all these symmetries, etc., etc.
Yeah.
Whereas
but some of this,
even particle physics have been inspired by P.W. Anderson's work when they wanted to really solve those riddles of particle physics. And I believe that if we can have a series of such beautiful lectures, maybe divided into parts, which you gave a good bird's eye view of symmetry and its both scientific and artistic implication, I would say. So that will be a wonderful thing to do this year particularly. And maybe we can also bring one person who can really talk about life and work of Abdus Salam in that context. Can we really dedicate that kind of a series of say 5 or 6 lectures on this aspect itself so that general awareness about all these ideas also come in our community particularly. Because, for example, your lecture is also something which will be available to the community a lot. We will put it on, it is already on the YouTube. We have seen it there also. But if that happens, I think all these beautiful books which Professor Bhole also talked about, and this while small, it's just 35-page book. It's not a very big treatise on symmetry, but he talks about very many things around sculptures, visual things. Well, mainly he focuses on visual things. But I think in physics, we consider him as a father of bringing symmetry into the physics itself.
Yes.
So all those ideas are very fascinating, and I think we need to really let our even undergraduate students and PG students know about these things.
Yeah,
thank you very much for your lecture. And
thank you, sir.
Maybe if somebody can talk also about the book by S. Chandrasekhar on his lectures, which where he talked about beauty in the work and the comparison of Newton and a musician was also there. Shakespeare was also there. He made a comparison between Beethoven and Newton, and the third thing which I am just said. All these things will be very relevant for our community. This is what I feel, and I wish if we can really chalk out. And I'm sure that Mumbai sub-RC is truly taking all these things seriously. And this lecture itself
That's thanks to Mahesh.
dedication to Professor Dharkar, who was a passionate person who interacted with community in a very big way.
Yes.
I really enjoyed your lecture.
Thank you, sir. Thank you. I just wanted to make two comments. Derek famously said that it is more important to have beauty in your equations than have them agree with the experiments. The experiments will follow if your theory is beautiful enough. When he tried to fit the black body radiation and was not getting things correct, he emphasized the idea of beauty
Am I
in
audible?
the physical equations. Sorry? Yes, sir.
Am I audible?
So, and the second thing is crystallographers. I don't think they take the idea of symmetry as repetitivity,
Hello.
but they could probably get some more information.
Am I audible?
Yes, sir.
Yes, sir. Yes.
Yeah. Okay. So what I was saying was that this lecture is a tribute to Professor Dharkar also, who was very passionate about bringing out new things before the community. Very passionate person. So I thank you very much, Professor Vaya. There is another suggestion which I can give.
Yes, sir.
Because as a president, I keep on feeling all those things. So I must really convey that in this particular lecture. We have physics education journal also, which has been revived now.
Okay.
And we can even, publish this lecture there as a special contribution from your side. If that can be made possible, I think it will be wonderful.
Oh, it would be a pleasure for me to write this article lecture down. It would be. Thank you very much, sir, for the invitation.
Thank you.
Mahesh, you want to add?
One more question is there.
Yeah, in the black, there are questions that information. So there is this quantum mechanical law which says that information cannot be destroyed, and there has been a lot of argument about what happens to information that is put back into a black hole, and whether you can retrieve that information or not. The jury is still out on that. It is not absolutely clear because the thermal radiation completely destroys information. So, for example, in a classroom, when I speak at the end of my lecture, if you know the exact movement of each particle, you should be able to recreate my entire lecture. But that doesn't happen because the classroom reaches a thermal equilibrium and that white noise will destroy all information. So the question is whether material falling into black hole eventually returns into a thermodynamic equilibrium, in which case no information will be lost, or whether like quantum mechanics, like the charge we suspect, it will hold on to that information. And if it holds on to that information, then Hawking radiation will not be symmetrical. It will depend on which kind of particles in that inner sphere is actually controlling that particular photon that is coming out. But jury is still out on whether why black holes destroy information or whether they still manage to send it back to the universe, as it were. Okay, Mahesh says that is it because symmetry of space breaks down at the smallest level? You actually have a very unpleasant situation, because at the smallest level you end up with quantum mechanics, and because of the fact that mass is energy, energy has wavelength and frequency. So there is a fundamental uncertainty in localization. Given that there is no such thing as infinitely precise information. Newton's laws depend on infinitely precise information, but quantum mechanics tells you that at some level the precision will be lost. At worst at an uncertainty principle level, but much earlier than that information will be lost. And therefore you cannot give infinite precision. The example that I like to give is that if you have a dark room in which there are people and you want to know who is where, you would send a person to go there who would sort of feel his way around, and as he touches the people, he would note down that this is where I met somebody and this is where I met somebody. And then he would come back and tell you. But in the very process of trying to find out who is where, he spoils the arrangement. When the probe that you are using has the same energy as what you are probing, all bets are off. And once all those bets are off, essentially you end up with information loss and information uncertainty. And that information uncertainty at the smallest level, I think, is a more serious problem than the question of localization. Localization, anyway, cannot be done beyond the wavelength of the object, its energy equivalent. So that would be my answer. And therefore, symmetries in that sense would not exist at that level, in the sense that reversibility will not exist at that level. Time reversibility will not exist at that level, because among the many possible outcomes of quantum interaction, which one actually happened, we really do not know at this stage. Since human beings sorry?
Please go ahead. There's one more question in the chat.
Yes. So Sian has a question saying that because human beings have general knack for symmetry, would that be a bias in research? It probably would be. Human beings, see, we were never designed to do all these kind of things. We were designed to eat, not be eaten, and survive. And the strongest senses we have are visual senses. And visual senses pick up symmetries. So we are biased towards visually understandable objects, but nature is not bound by making itself understandable to us. So, for example, if you go and ask quantum physicists to give you a physical picture of the universe, he'll just laugh at you and say that these quantum systems obey these equations. Take it or leave it. I mean, if you can't get a physical visual imagination, that is your problem. But we still search for symmetries. We search for even for solar system, we talk about onion skin kind of model, which is way inaccurate to the reality. But we need visualizability, and that is our compulsion. It's probably does drive a lot of biases. So there are books like go what that Bach and Godel, and there is a third name to it, the musician. And he talks about how maybe nature is not got anything to do with the classical equations that we write down, but it is probably a question of symmetries and resonances. Escher, Godel, and Bach, which talks about the fact that, look, nature may be just a question of resonances of various forces and various time events, and that our division it into classical mechanics, etc., may be just a question of our biases. And Escher, Ayush has pointed out that. So there are ideas like that. Then there are ideas of automatons, which are completely different ideas. It's a new kind of physics that somebody has tried to propose, has its own set of alternative ideas of what reality is. And maybe we are so biased by what we can see and what we can experiment with it, is that somewhere down the line we have missed completely different way that nature works, because nature is certainly not required to be understandable to us. So there are ideas like that, but we go by what we can prove rather than what we can imagine, because we know from history of science that many cases what we have imagined has turned out to be not true, and nature just didn't choose that way of doing things. The classical example was that heat was thought to be a liquid and it turned out to be not a liquid, and so on. So yes, I mean, at this level, then you come up with these questions of whether physics and physics is invented or discovered is a question you can actually ask. And there are people who will tell you that it is invented and not discovered. And most people would argue that it is discovered and not invented. But there is definitely a small group that will argue that it is invented and not discovered. Mathematics has this eternal problem, whether it is invented or discovered.
Yes. Yes, thank you. I think it's
Thank
time to propose formal vote of thanks. I thank you first, Dr. Mayank Vaiya, for taking your time out preparing this presentation. It was really wonderful. And I also thank Professor Ahluwalia for being present here, and Rekha Ghorpade. They both are busy at the national level, managing IIPT. And thank you very much for being here. And it means a lot for us working at a small level. Then within Mumbai IIPT, of course, Mahesh Shetty. Then Kamala Madam, who's not here, Leena Madam, and also, of course, Sushmita Madam. And foremost, Bode sir, thank you all for being there in organizing, planning, and execution of this meeting. And of course, I thank all the audience. Without that, we couldn't have conducted this event. Thank you very much for